Tonight, we're going to talk about the edge of the universe. And I don't mean the boundary of the solar system, or the edge of the Milky Way, or even the furthest galaxy ever photographed. I mean the actual edge. The place where the observable universe ends. The boundary beyond which no signal, no light, no information of any kind has ever reached us and never will. Because here is what most people don't know about that boundary. It is not sitting still. It is running away from us. And it is accelerating. And the deeper physicists look into what is happening at that edge, the more they realize that the universe is not quietly winding down towards some distant ending. It is heading somewhere specific, somewhere we can calculate. And the destination, it turns out, is one of the strangest and most unsettling things that physics has ever produced. Let's start with something that seems simple, but is actually one of the most important ideas in all of cosmology. When you look up at the night sky, you are not seeing the universe as it is. You are seeing it as it was. Light takes time to travel. The light from the moon left the surface about 1.3 seconds ago. The light from the sun left 8 minutes ago. The light from the nearest star beyond our sun left about 4 years ago. The light from the Andromeda galaxy, the nearest large galaxy to our own, left about 2.5 million years ago. When you look at Andromeda with binoculars on a clear night, you are looking at light that began its journey before our species existed. Now extend that logic outward. The further away something is, the older the light we receive from it. The most distant galaxies we have ever photographed with the James Webb Space Telescope are so far away that the light reaching us left them when the universe was only a few 100 million years old. We are not seeing those galaxies as they are now. We are seeing them as infant structures, barely formed, in a universe that was still figuring out what it wanted to be. This is not a limitation of our telescopes. It is a fundamental feature of reality. Light has a speed limit. The universe has an age. Those two facts together create a horizon, a bubble around us beyond which we simply cannot see, because the light from those regions has not had time to reach us yet. That bubble is what we call the observable universe. And its edge, its horizon, sits roughly 46 billion light-years away in every direction. Now here is where people immediately get confused. If the universe is only 13.8 billion years old, how can the edge of the observable universe be 46 billion light-years away? Shouldn't the furthest light we could possibly receive have traveled at most 13.8 billion light-years? The answer is that space itself has been expanding the entire time. While the light was traveling toward us, the space it was traveling through was stretching. Imagine you are walking toward a destination that is slowly moving away from you. You will eventually reach it, but the distance you cover will be greater than the distance the destination was when you started walking. The light that left the earliest galaxies started its journey when those galaxies were much closer to us than they are now. In the 13.8 billion years it took that light to arrive, the universe expanded so dramatically that those same galaxies are now 46 billion light-years away. This expansion is not the galaxies moving through space like billiard balls. It is space itself growing. The fabric of the universe is stretching, and everything embedded in it is being carried along for the ride. And here is the crucial thing. That expansion is not slowing down. It is speeding up. In 1998, two independent teams of astronomers made a discovery so unexpected that it won the Nobel Prize. They were studying Type 1a supernovae, the same cosmic standard candles used to measure the Hubble constant. and they expected to find that the universe's expansion was slowing down over time, gradually braked by the gravitational pull of all the matter inside it. What they found instead was the opposite. The expansion of the universe is accelerating. Something is pushing space apart, faster and faster, with no sign of stopping. That something has been given a name: dark energy. But the name is essentially an admission of ignorance. We call it dark energy because we can see its effects, we can measure its strength, but we have no idea what it actually is or where it comes from. It appears to be a property of space itself, an energy embedded in the vacuum, present everywhere, constant over time, quietly and relentlessly driving the universe apart. Dark energy makes up approximately 68% of everything in the universe. And the matter you can see, stars, planets, galaxies, gas clouds, everything detectable, adds up to about 5%. The rest is dark matter and dark energy, two enormous unknowns that between them account for 95% of the content of the cosmos. And dark energy is winning. Gravity pulls inward. Dark energy pushes outward. And at the scales of the largest structures in the universe, dark energy is decisively in charge. This is where the edge of the universe starts to get genuinely unsettling. Because if dark energy is real and the expansion of the universe is accelerating, then the observable universe is not a fixed thing. The boundary is shrinking, not in the sense that the bubble is physically getting smaller, but in the sense that galaxies that are currently within our observable universe are being carried away from us by the expansion of space faster than light can travel between us. And once a galaxy crosses that threshold, once it is receding faster than light, the light it emits will never reach us. It has effectively left our universe, not by moving somewhere else, by the space between us growing so fast that no communication of any kind is possible. Right now, every galaxy beyond a certain distance, roughly 16 billion light-years away, is receding from us faster than light. They are not violating the speed of light. The speed of light is a local limit, a limit on how fast things move through space. But space itself can expand at any rate, and at large enough scales, it is expanding faster than light. Those galaxies are already beyond our reach. We can still see them, because the light they emitted long ago, when they were closer, is still arriving. But any light they emit today will never reach us. We are receiving their old messages, but their new ones will never arrive. Think of it as letters crossing an ocean. The letters already in transit will eventually arrive. But if the ocean is growing faster than the ships can sail, any letter posted today will never make it across. The galaxy is still there. We just cannot communicate with it anymore. And the acceleration is not stopping. As time goes on, more and more galaxies will cross that threshold. In 1 trillion years, if there are still beings here capable of looking up at the sky, they will see almost nothing. The Milky Way will have merged with Andromeda by then, a process already underway, and the combined galaxy will be surrounded by the local group, the small cluster of galaxies gravitationally bound to us. But beyond the local group, the rest of the universe will be gone. Not destroyed, just unreachable. Every other galaxy will have been carried so far away by the expansion of space that no light from them will ever reach us again. Those future observers will look at the sky and see only their own galaxy. They will see no evidence that there is anything else out there at all. If they develop physics and cosmology from scratch, they will have no way of knowing that the universe was once full of billions of galaxies in every direction. They will not be able to make the measurements we can make, because the evidence will have been erased by the expansion of space. The universe will have hidden its own history from them. We are, right now, in the privileged era of cosmic history, the era where enough of the universe is still visible that we can piece together where it came from and where it is going. 1 trillion years from now, that will be impossible, and the window is closing. Let's go one step further, because this is where the destination becomes truly strange. The logical endpoint of accelerating expansion, run forward far enough, is a state that physicists call the heat death of the universe. But heat death is a misleading name. It does not mean the universe burns up. It means the opposite. As the universe expands, it cools. Energy spreads thinner and thinner across a larger and larger volume of space. Stars burn through their fuel and die. The last star in the universe, a dim red dwarf billions of times longer lived than our sun, will eventually run out of hydrogen and fade. After that, the universe will be populated by stellar remnants, white dwarfs, neutron stars, black holes, slowly cooling in an expanding darkness. The white dwarfs will cool over trillions of years into black dwarfs, objects so cold they emit virtually no radiation. The black holes will evaporate. Stephen Hawking showed in 1974 that black holes are not perfectly black. They emit a faint trickle of radiation, now called Hawking radiation, and over an almost incomprehensible period of time, far longer than the current age of the universe multiplied by itself many times over. Even the largest black holes will evaporate completely, releasing their mass as a final burst of low-energy particles. After that, there is nothing left to happen. The universe will be an infinite, cold, dark expanse of space, expanding forever, containing nothing but the faintest possible traces of radiation too thinly spread to interact with anything. No heat gradients, no energy differences, no way for anything to happen. Not a bang, not a crunch, not an explosion, just an eternal, expanding, featureless dark. Physicists call this maximum entropy, the state where everything is perfectly, irreversibly disordered. Nothing can change because there is nothing left with the energy to change. Now let's be honest about what we don't know, because there is a great deal. Dark energy might not be constant. The measurements we have suggest it is, but those measurements are not precise enough to rule out the possibility that dark energy is slowly changing over time. If it is growing stronger, the end of the universe could be far more abrupt than the slow fade of heat death. There is a scenario called the Big Rip, in which dark energy grows so strong that it eventually overcomes not just the gravity holding galaxy clusters together, but the forces holding galaxies together, then solar systems, then planets, then atoms themselves. In the Big Rip, the expansion of space accelerates without limit until it tears apart every structure in the universe down to the subatomic level. The end is not a quiet fading, but a violent unraveling of everything that exists, including the forces that hold matter together. This scenario remains speculative. Current measurements do not strongly support it, but they do not rule it out either. There is also the question of whether the universe is actually infinite. If the universe extends beyond the observable bubble, and there is no reason to think it does not, then there is more universe out there, unobservable to us, beyond our horizon. If the universe is truly infinite in extent, then the strange fate awaiting our observable patch may not be the whole story. An infinite universe contains infinite possibilities, and some of what those possibilities allow is genuinely difficult to think about clearly. Some cosmologists have proposed that in an infinite universe, given enough time, unimaginable amounts of time, far beyond what heat death requires, thermal fluctuations in the quantum vacuum could spontaneously produce, by pure chance, a temporary low-entropy region, a place where, for a brief moment, the laws of thermodynamics run backward and order emerges from chaos. Not a whole new Big Bang necessarily, but something, some structure, some event. The universe, left long enough, might not be as final as it seems. Here is what strikes me most about all of this. We are standing at a moment in cosmic history that will never come again. The universe is currently at a scale and in a configuration where it is possible for beings like us to look outward and see enough of the larger structure to understand what is happening. We can see the edge. We can measure its recession. We can calculate its eventual disappearance. We can work out what comes after. In 1 trillion years, that opportunity will be gone. The evidence will have been erased. Whatever beings exist then, if any do, will be cosmologically blind in a way we are not. They will inherit a universe that has hidden its own origins and its own structure behind an impenetrable wall of accelerating expansion. We are the generation that gets to see it whole, or as close to whole as it will ever be. And what we see is not a static, eternal backdrop for human history. It is a dynamic, evolving, accelerating structure with a beginning we can trace and an end we can calculate. And the end, when it comes, will not be an explosion or a collapse. It will be a silence so complete and so vast that the word silence does not really cover it. There is a certain discomfort in looking at that future and sitting with it honestly. The universe is not built around us. It does not accommodate our desire for permanence. It does what it does at the scale it operates at, ion timelines that make human history look like a single frame in an impossibly long film. But here is what I keep coming back to. The universe does not know it is doing any of this. It does not contemplate its own expansion or mourn the galaxies it is losing over the horizon. The contemplation is happening here. On this pale blue dot, inside this unremarkable galaxy, within this below-average region of the cosmic web, there are beings who have looked outward far enough to understand what they are inside, who have measured the edge and tracked its recession, who have calculated the end and thought carefully about what it means. That is not a small thing. That might be the most extraordinary thing in the observable universe. The edge is running away from us. The darkness is coming, eventually, inevitably, on a timescale so vast it is essentially meaningless to daily human life. But tonight, the universe is still visible, and we are still looking. Good night.